Okay, so now we're going to move on to the second page. Okay, and so the question is asking about a domain. So let me give a domain here, omega. Again, all of my omegas are going to look kind of like amoebas. If we were doing this in R3, I would be thinking about a potato. And we're going to have a boundary. This is the boundary of omega. And now at every point on the boundary, if the boundary is nice, which is what we're assuming it is, at every point on the boundary, there's two important vectors. Okay, there is going to be the tangent vector, the unit tangent vector. Let me make that a little more tangenty looking. There's going to be the unit tangent vector like this, which I will call t, and the unit normal vector, which is perpendicular to the tangent vector, which I will call frustratingly either capital N or lowercase n, sometimes with a hat, sometimes without a hat. Sorry. That's what we got. And so we want to know, so first of all, let's try to talk a little bit about what's going on with these vectors, and then let's try to get a computation for the vectors. So what we're going to be dealing with in this class are going to be like the flow of things. One of the things we're going to be dealing with this class will be the flow of things. So imagine I have some quantity there's a concentration of a quantity that I'm modeling, and it's flowing through R2, and this is an arbitrary domain in R2. And let's say it's flowing, like this is one of the curves along which it's flowing. And it's coming out the boundary at this point. Okay, now there's a line like this all over the place. But only the component, if I have a velocity field, let's say something like v of xt, if I have a velocity field and whatever it is going along this velocity field here, then the only part of the velocity field that is transporting material outside of the domain omega is going to be the component of the velocity field that's parallel to the normal vector here. So if I draw the normal vector like this, and let's say this point here is AB, then it's just going to be the dot product, it's just going to be the projection of V onto N. So it's going to be the dot product of V with N times N hat. That's going to be the component of the velocity vector in the direction of the unit normal vector. Okay, that's the only component of the velocity vector that is bringing material outside of the domain. The tangential component at that point here is not moving material outside of the domain, it's moving it in the direction of the domain, kind of going alongside the domain, I guess, but it's not going outside of the domain like this is. Okay, so how do we actually compute what these vectors are? Tangent and the normal vectors, I'm going to assume that the boundary of omega has a parameterization given by x of t, y of t. Okay, making sure that you can see that. So the tangent vector is going to be pretty simple. The unit tangent vector is just going to be the velocity vector of r, but divided by its magnitude to make it have unit length. So this is going to be x dot of t, y dot of t, divided by the magnitude of this vector, so divided by the square root of x dot of t squared plus y dot of t squared. And I'm just going to write this, so this is just r prime of t over the magnitude of r prime. Now the normal vector is going to be perpendicular to t and have unit length. The normal vector is perpendicular to t and has unit length. Now there are two choices that we can take here. There's exactly two choices that we can take for a vector that is perpendicular to t and has length 1. The first one is going to be minus y dot of t, x dot of t, divided by the magnitude. Okay, why is this perpendicular? Well, the dot product of this vector and that vector are 0. I've got minus y prime times x prime plus y prime times x prime. So minus y prime x prime plus y prime x prime is 0. And the other choice is just to put the minus sign there. So it's y dot of t minus x dot of t, and then dividing by the magnitude. Okay, so which is the one that we want to take? So over here, I have my normal vector pointing out, and it's important that when I did this computation here to talk about the velocity taking the material outside of the domain, it was important that n was pointing in that direction for this computation to tell us how much was going outside of the domain. If it was going that way, it would tell us how much is going inside of the domain. But it's going that way, so it's telling us how much is going outside of the domain. So what we want is not just any normal vector, we want the outward pointing. We want the outward pointing normal vector. And there's a number of ways to figure out how we can figure out which normal vector to take. So let's look at this point here, where I've got a horizontal tangent vector, and I've got a vertical normal vector. Okay, so the tangent vector, if the tangent vector is horizontal, it means that the x component is going to be negative. If it's horizontal and pointing in that direction, the x component is negative and the y component is 0. Okay, for the normal vector, the x component is 0 and the y component is positive. Okay, now if I look at my two choices for normal vector over here, the y component of both choices of the normal vector is going to be the x component of the tangent vector. Okay, so this says the x component of the tangent vector is negative. Okay, but the y component of the normal vector is positive. So it says the x component of the normal vector is negative, the y component of the normal vector is positive. So if I chose this, notice x dot would be negative, because the x component of the normal vector, that's just x dot, that would be negative. On the other hand, if I choose this one, if the x component of the normal vector is negative, when I multiply it by -1, it's positive. And so it tells me that this is the thing that I should use as the outward pointing normal vector. Okay, so I'm going to record that information over here. So this is what t is. And then n is going to be equal to y dot of t minus x dot of t divided by the square root of x dot of t squared plus y dot of t squared. Okay, and so that is the unit normal vector. Okay, so the last question is something about this. If I have a function, what does this mean? What is this? This means the derivative, I'm looking at a point here on the boundary, it means the derivative of phi in the normal direction. Okay, so if I have a point here, this is just going to be the directional derivative of phi in the direction of the normal vector. And we can compute this as following. This is going to be the gradient of phi dotted with the normal vector. Okay, so that's all that we have for this video. We're going to be applying these to PDE things in the upcoming videos.